Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside. We are going to look at Chapter 8, the beginning of Chapter 8, Section 8.1 in the Big Ideas Math Integrated Math 2 textbook. The whole chapter is on similarity. This first section is on what is known as dilations, and of course, the lecture portion will teach you all about what dilations are and what we have with it. Now, knowing what dilations are and having looked at the sections for a moment, and I'll tell you more about it in a second, but knowing what this chapter and this section stuff is all about, dilations is a bit of a precursor into what similarity is all about. In other words, you'll be creating similar images and maybe not necessarily knowing it. The word similar isn't yet thrown into the mix until Section 8.2. I'll probably be saying the word here and there. I might even let you know what it is as it happens, but the fact that you're dilating kind of is just a manipulative of sorts. It's a transformation, and you're creating similarity along the way. So this is a precursor to similarity. It's not really a part of what similarity is. Don't get me wrong, it creates similar objects, but when we start talking about similarity, it's within its own rights and not even talking about dilations anymore. So that's the first thing. Second thing is, I've seen a little bit of the section only because I've already assigned this section to my students. So I am aware, I haven't tried the problems, but I am aware that there will be construction. I am aware that there are some graphs that are outside of our standard window range. So in the PDF down below, when I do attach this graph paper thing, please understand that sometimes I'm going to change the scaling of the graphs, maybe to go by every 2s or every 3s or something like that, because I'm aware that that happens. I don't really know to what extent. I haven't done the problems yet, but I'm going to do them with you right now. Once again, check out the description section down below. Check out the PDF of this actual textbook problem set, as well as timestamps for every part that I do for this thing. I begin with a lecture, then I'll do the problems themselves. It goes to 50 some odd problems. Let me see. It goes to 51 problems here overall when we get to that stage. All right. Without further ado, guys, let's go ahead and get started. We will identify and perform dilations. We'll solve real-life problems involving scale factors and dilations. And probably no proofs. I can't guarantee it, but probably no proofs in this section. We will be doing proofs down the line in this chapter with 6 sections total. Once we get near the end of this chapter is where the chapter really takes form, because sometimes the end of the chapter is more like excess stuff. The end of the chapter is really where we start to get into, like the last few sections, where we get into the concepts of similarity and what we have to use in future chapters as needed. Okay, core vocabulary, new word here, dilation. There's also center of dilation, an important part within the transformation itself, something we won't use after this section, really. Scale factor, enlargement, and reduction. These are all kind of within the same bit as well here. Okay, identifying and perform dilations. What is a dilation? It's a transformation in which a figure is enlarged or reduced with respect to a fixed point C called the center of dilation and a scale factor K. Well, we just used every single target word here that we need, which the ratio of lengths of the corresponding sides, which is the ratio of the lengths of the corresponding sides of image and pre-image. Okay, what did they just say there? What happens is, and I like to think of it like a flashlight, which I don't have, but if you take a flashlight, shine a piece of paper against a wall, then say the paper is your pre-image, it's a pre-trans. And by the way, if you've used transformations before, think about reflections, rotations, and translations. Right, you have a pre-image and an image before translation, before transformation, after transformation. A dilation changes the size of your object, but if your flashlight's the center of dilation, where the light beams from, and it takes a piece of paper and then it casts it on the wall, maybe twice as big, 3 times as big, 4.5 times as big, something like that. It can enlarge that object into there, going from the center outward. And so you're going to see instances of it. Pretend like this triangle was enlarged onto this thing right here, and you have these lines coming out from the center like it's a flashlight, beaming light, and then you have these corresponding points with it. So that's what a dilation is. It can also reduce, which isn't as good with a flashlight example, but it can also reduce inward. So a dilation with center of dilation C and scale factor K, that's the number that you got to multiply it by to make it that many times bigger, maps every point P in a figure to a P prime. So the following are true. If P is the center point, then P equals P prime. You know, I think this is better off that I'll read it, but it's better off that we see it when there are examples of it. If P is the center point C, then P is P prime. If P is not on C, then the image of P prime lies on ray CP. So you can see when I cast this shadow, this light beaming, it goes through P and onto this P prime right there. They're all in the same ray together. They go on that same line. You can draw a straight, they're collinear. They're collinear. You can draw a straight line through them. Same with Q and R. And there's a scale factor as well. How many times bigger is CP prime than CP? You divide this by that to figure it out. Like 4 divided by 2 is 2, things like that. Angle measures are preserved. Now, this is one of the bigger concepts of similarity, that this angle is the same as it is, even though it got bigger as an object. These angle measures are going to be the same here, and these angle measures are going to be the same there. So angle measures are preserved. A triangle still adds to 180 degrees. It's not like it suddenly becomes 360 or something. It's just a bigger triangle, and it's a similar triangle. A dilation does not change any line that passes through the center of dilation. So it still goes through that center. A dilation maps a line that does not pass through the center of dilation to a parallel line. In the figure above, the lines are parallel here. So PQ, let me get rid of some of these things here. So these guys are parallel here. P prime and P prime Q prime. P Q and P prime Q prime. R Q and R prime Q prime. And these guys, they're all parallel. We're going to see those on graphs. When the scale factor k is greater than 1, a dilation is an enlargement. When k is between 0 and 1, a dilation is reduction. K can be negative on graphs. We're going to see that. And then if it's, a -2, it's still an enlargement, things like that. So k being 2 means your object becomes twice as long in every which way, and it's twice as far out from the center. That's an example of something like that. When k is like 0.5, 1/2, then it's half the size. So here are some examples of dilations here. Here's a paper clip that gets enlarged from P to P prime. You can see the distance from C to P is 8 and from C to P prime is 12. So we can determine whether it's an enlargement or reduction. I called it an enlargement. Now, being an enlargement, the K value is going to be a number more than 1. We're going to divide 12 by 8 to figure out what that scale factor is. It's 3 over 2. 3 over 2 is also 1.5. I'm multiplying this by 1.5 to become that. The distance from the center is 1.5 times farther out, and the object is also 1.5 times bigger in any which way that you imagine it. This is 1.5 times bigger there, or 1.5 times wider, and all that kind of stuff. Everything's 1.5 times bigger in that way. Now, you have a different version on this next one where you go from a bigger paperclip to a smaller one, going closer toward that center. It's like shrinking into it. It's almost like a... I can't get a better example for transformation purposes. Like a black hole, but I guess you don't really shrink toward it. You just go closer to it. Going closer to the center, we go from a length of 30 to a length of 18. This is a reduction. We are going to divide 18 by 30. You divide the prime by the original. So 18 divided by 30 reduces to 3/5, 0.6, 60%. This guy is 60% the size of this guy when it comes to length in comparisons. It's 60% closer. 40% closer. Is 60% the distance of what that is. All that kind of stuff. So we'll see a bunch of examples. Let's do coordinate rules for dilations. These are pretty straightforward. Let me move myself here. It's hard to mess up as well. You have a point that's on some xy. If our dilation is centered at the origin 0, 0, everything's going to grow out from there a certain amount, k times further out, and it goes in both directions, both dimensions, x and y. X gets multiplied by k, y gets multiplied by k. And you get this dilation. Everything becomes this many times bigger or smaller, and this many times farther or closer to the origin. So here's an example. If you have a scale factor of 2 from these original points A, B, and C, you identify where those points are, or they give them to you, and we double them. From 2, 1, the 2 and the 1 get doubled to 4, 2, 4, 1 get doubled to 8, 2, and 4, -1 get doubled to 8, -2. So not only is this new triangle twice as big, or excuse me, I should say it the other way. Not only is this triangle twice as far out from the origin as the original object is, but the triangle is now twice as big. And what's nice, once again, is what they said is you can draw straight lines going through these as if they're collinear. It's like casting a shadow out. Do you need to do it anymore? No. But it kind of gives that idea, and your center's at the origin. So here's another one, but this time the dilation is going to be a value that's less than 1. It'll be 1/3, so it'll be a reduction. This original quadrilateral, this blue guy right here, goes from blue to this red, and it becomes 1/3 the size not in area. I should be careful when I say size, but 1/3 the lengths all throughout. So I can draw lines out to each of these corresponding points and through there. It's a little different when it goes through the origin itself, but M prime is on the same line as M with the quadrilateral, things like that. So everything's 1/3 the size in that way, and even these lengths become thirded, which means from K to L, that distance is 3. Now this distance is 1, becomes 1/3. Just multiply by 1/3 divided by 3. And if they give you nice numbers, then you should be able to plot them. But they're obviously going to do ones for us where they seem to go outside the window range, which is a little, yeah. Now, I did warn of compass construction, so we're going to see some of this as well. To construct a dilation, it's pretty straightforward. Remember, you cast a shadow outward, you draw the lines through these points. Somewhere on this line for CP, or this ray, will exist P prime, somewhere. Whatever the scale factor is. If the scale factor is 2, we're going to deal with that, but it's twice as far out. And on Q prime is twice as far out, R to R prime is twice as far out. The compass part's really easy. What you do is you change your compass width to whatever CP is, and you double it. So here's CP, that's one of them. Do a second one, boom. So these are the same length here. That's double the distance out. You don't do 2 more, you just do 1 more because you're doubling it. And Q to Q prime, change your compass width there, and R to R prime, change your compass width there. And then you connect these dots. Connect these dots at where the arc intersects with the line that it crosses through, and there's the new dilation and enlargement, twice as big, twice as far away, and there it is. Now, there is a way to do reductions as well. I hope they give us clean enough numbers, because to do like half the distance, it's best to get like midpoints, perpendicular bisectors, stuff like that, from old compass stuff we've done in the past. We'll take care of it if it shows up. I did mention you can have K values that are less than 0, that are negative. So if you have a pre-image here, scale factor of K maybe twice as big like this, and then a -2, for example, can look like that, where if I drew lines, keep in mind that a line would go through something in its corresponding point. I don't really know if this lines up perfectly. And of course, the way my thing snaps won't actually totally work like that. But then it can also go the other direction. It can hit the corresponding points on the other side. I don't really think that this thing's to scale, so it doesn't work. But this should be able to go basically through the center and out the other side like that. So it's like it inverts out the other side, like a camera obscura. If you know what that is, you can Google that. Basically the way the camera works, the way that your eye works. Lets light in and comes out the other side to your brain. So negative scale factors, I mean, listen, it's as simple as multiplying by your negative number. -4 times -1/2 is +2. -2 times -1/2 is +1. This one should be to scale, so I can draw these lines to corresponding points. And look as they go through the origin. Here's a great example of going through and out the other side. Becomes a rotation and a reduction at the same time. Pretty neat. Finding a scale factor in real life problems, let's take a look at what they say here. You have, and I'm sure they're going to talk about area comparisons in the like critical thinking, which I can then explain more. But I have something that's 1.1 inches in width and it goes to 4 inches. It must be a square photo. The scale factor is 11 to 40. Oh, maybe this is the bigger one and then it shrinks. I should read this. You're making your own photo stickers. Your photo is 4 inches by 4 inches. The image on the stickers is 1.1 and 1.1. What's the scale factor? Yeah, so here's the prime. Here's the transformed one. Here's the original. So you got to multiply everything by whatever 1.1 over 4 is, the equivalent to 11 over 40. Try to give you an exact number. 27.5% of what it was before. Finding the length of an image. You are using a magnifying glass that shows the image of an object 6 times the object's actual size. So now the K value would be 6 in this case. And they set up kind of a thing. Listen, a lot of these things, by the way, guys, if you know what proportions are, everything can be set up like a proportion. Later in this chapter, proportions are going to be a huge part of what we set up. And this is ideally what we're doing. When you take the image length divided by, because it's 6 times bigger, image length divided by the actual length, it should be 6. When I divide it should be 6, so you multiply both sides by 1.5 and you get 9. So while the original spider thing is 1.5 centimeters in length, now through the magnifying glass the image becomes 9 centimeters in length, becomes 6 times bigger. You multiply by 6. More examples. Here's something that I just wanted to show you right here. A dilation needs to expand in all directions together, enlarge or reduce. Basically grow out or shrink from an individual center, all dimensions. So you can't just change one thing and then just change the other thing, because as you can tell, angle measures are no longer preserved. B and B prime are two different angle measures. A and A prime are two different angle measures. It's not just a bigger version of that triangle. And the best place where you can find something that always has this kind of proper scale factor and dilation, not that everything has a center, but just in similarity, which we'll talk about more, are televisions. The television behind me has that 16:9 aspect ratio, 16 by 9. And your widescreen television probably does. My monitor is different. It's 21 by 9, but a lot of widescreen televisions have that, and that's a good example of it. All right, guys, let's jump straight into the problems where we have the vocabulary and core concept check, and then we're going to do the actual problem set. Let's complete the sentence. If P at xy is the preimage of a point, then its image after dilation centered at the origin 0, 0 with scale factor k, you're going to take, first of all, the point will now be called P prime, and the ordered pair will be k times x and k times y. You multiply both of those parts by that, and then you can get the actual point that it is. Which one doesn't belong? Which scale factor does not belong with the other three? Explain your reasoning. Let's say that A is the 5/4. That's a number that's more than 1, makes it an enlargement. 60% of something is also 0.6 or 3/5 or 6/10. I imagine that's going to be a B because that's different. 115% is more than 100%, also an enlargement, which is A. 2 is twice as large, also an enlargement. I'm going to call that A. So these are all enlargements. It says explain your reasoning. A is enlargements. And by the way, I often don't explain these, at least like this. So sorry if I forget to when they say explain. B is a reduction. Less than 1 versus greater than 1. What you're multiplying by for scale factor purposes. Now, 115% doesn't mean multiply by 115. It means multiply by 1.15. And 60% means multiply by 0.60. Things like that. Let me take out that 0. And that's the difference. 5/4, by the way, would be 1.25. And you can see the comparison. All right, guys, we're going to jump into the official problem set now. Get your stuff ready. And like I said, I haven't done the problems themselves, but I'm aware of some kinds of problems that exist, including compass stuff, including graph stuff where the scales might be a little wonky. We'll see what they look like. Let's go ahead and get started. Okay, let's start with problem numbers 3 through 6. In exercises 3 through 6, find the scale factor of the dilation, then tell whether the dilation is a reduction or an enlargement. Now on number 3, notice that P is in blue, P prime is in red. We're going from 14 to 6. Excuse me. My best way, and I'll probably write it differently after this, but my best way of saying this is you're taking that length of 14 and then you're multiplying it by some scale factor k to get 6. What is that scale factor? You divide both sides by 14 to figure that out. So k is going to be 6 over 14, but that also reduces to 3 over 7. This is a reduction. And, you know, I can state reduction and enlargement beforehand. It's probably better to do that so you know which way to divide almost. I know it's reduction because P is the pre-image, P prime is the image, P prime is smaller and closer to C, and that's what happens. And that's the only length that we're provided, but it still works. The dilation, this also means that this red is 3/7 the length everywhere of this guy. And it's also 3/7 the distance to C. In that way. So everything is 3/7 the size. That's how these things work. Okay, so hopefully you see what that looks like when you do that. Number 4. Number 4, it might make more sense once again to state what it is. It goes from P to P prime, blue to red. This is going to be an enlargement. Maybe I say that first, so maybe you even know which way you're supposed to set this up. I multiply 9 by some value k to get 24, so k is going to be 24 over 9. Now 24 over 9, divide those by 3 and you get 8/3. 8/3 is more than 1. That follows with the enlargement thing. So the algebra that I'm showing you there, I'm not going to show you each time. In fact, I'm probably going to stop showing you for the next 2 problems here because the book doesn't even tell you how to do it that way. But that gives you the better idea of what scale factor is all about, the fact that it's multiplying by something to make it happen. So on number 5, we see the length of 15 going from the center to P. And then 9, P prime, this is a reduction going from 15 to 9. You multiply 15 by something to get 9, so we divide 9 by 15 to figure that thing out. And if you weren't, and that divides by 3 as well. This is 3/5. And if you weren't sure which way you're supposed to divide, is it 15 divided by 9 or 9 divided by 15? That's why I'm saying ask yourself first whether it's an enlargement or a reduction. And we answer that based on going from P to P prime. Are we going bigger or smaller? So I feel like it's probably easier to answer that question first. Now, number 6 goes from just a distance of 8 to a distance of 28 from P to P prime, clearly an enlargement. So I will be dividing 28 divided by 8 to get K. And those can both divide by 4, and you get 7 over 2. Now, you might notice that I never once wrote the decimal version of it, which you could. I never once wrote the decimal or the mixed number. It's a fraction, and I simply reduced it. And I recommend you do that. I wholly recommend you just write a reduced improper fraction. It'll help most when you have to do things with proportions later, and when you have to multiply things that might not be so easy to do. Okay, guys, we're diving straight into construction here on number 7 through 10. Now, fair warning on the construction things as well. You might need more room than you think, and I need to say that to myself when doing these problems as well, because I need to be able to fit this on this entire thing. So I'm really going to shrink this image quite a bit to answer some of these things here. So on number 7, I need to enlarge, and I hope this is small enough. I need to enlarge this. I know this because K is 2. So K equals 2, center C, and K equals 2. I need to double the lengths of everything on here. So the first thing I'm going to do is draw lines outward, and I'll go ahead and kind of fade it. But I'm going to draw lines outward from C through L. Oh, this can't go straight. I don't know how to explain it, but this thing snaps. You can snap, snap, snap. I can't do anything about that yet. I got to think about it. Now, by the way, if you're wondering what I do with the P, I just ignore it right now. P is going to be used for a later problem. But I need to extend these lines outward so that I can get something that'll resemble an enlargement. I don't know how to deal with L because I can't. Okay, I think I know what I'm going to do. Problem is how these things snap. Give me one moment as I take everything, group it, and rotate it. Give me one moment. I'm going to rotate it. Nope. I didn't get the object itself. Take everything, group it, and rotate it. Because it snaps at horizontal and vertical lines. So if I make it non-horizontal or non-vertical like this, then I can actually get what I'm trying to do. See? Now I can actually get on it there. Of course, it snaps differently once I let go. I hate that it does that because it takes time out from us. But that's what you guys are going to do, guys. Take a ruler and draw it straight out. And by the way, you may be asking this. Mr. Robinson, why don't I just use a ruler to measure things twice as big? Oh, shoot. Okay, it's not perfectly on the line, but that's... Oh, none of these are perfectly on the line anymore. Mr. Robinson, why don't I just measure everything twice as big with a ruler? The idea is... Oh, this doesn't... I'm sorry. This thing gets all wonky when I rotate it back. I don't know what to do with that. Even now... Okay. This is taking more time than needed, but I get to talk about this thing. So what was I saying? Mr. Robinson, why don't I use a ruler to measure these? They're not assuming you have a ruler. Okay. I said straight edge. If I said ruler, I didn't mean it. A straight edge. An ID card can be a straight edge. A piece of paper can be a straight edge. They don't assume that you have ways to measure lengths, and even if you did, what if it was at, you know, a weird number that you have to then double? We're using the compass for this thing. Okay, that's the bottom line. So sorry about that setup, guys. This thing's going to take some time. I mean, that's the bottom line for me using this computer software. There's no other way I could have done what I was doing and just talking through it. Okay. This part's going to be pretty straightforward, though. What I'm going to do is measure out these distances for L, like that it was overshot, for example. I need to measure out the distances for L. I'll keep it kind of thin looking. And N and M, and then I'll double it. Now, I'll go as close as I can. For example, this thing snaps in a certain way. You can see that right there. About as close as I can get to this thing. I'll just go a little bit farther out like that to make this thing here. So that was one of the lengths. So here's a second length of that thing. And where that... Oh, it snaps again. But that's okay. Where that intersects is going to be it. Double the length. Let's do the same thing now for N. I'm going to grow out to this width. Like that. And now let's go ahead and double that out. Like so. Boom. I don't really need that first width. It was the second one. But I like to use that in case I need to triple widths and things like that. For M... Let's figure out this one here. It's probably a little too far out. Or, okay, that looks pretty good. So there's one length and go out to that point. And let's go ahead and do one more of those. Boom, like that. So let's get rid of that one arc, otherwise I might confuse you with what I was doing on it. So these three arcs where they intersect are the points where L prime, double the length out from C, N prime, and M prime exist. When we connect those dots, see, here's the thing. And I didn't really make mention of it. It's probably assumed to be true. Assumed to make sense, which is also true for other transformations that you do, especially on graphs, like rotations and reflections and stuff. Oh, this has a snap issue too. These vertices are not the only thing that got extended out. Every point on here did. This point right here got extended out to right there, right? But I only need the three that are vertices because I can connect the lines after that and then make the new diagram as a result of it. This thing is not only twice as far out, but it's also now twice as big. So everything else, Ln, L prime N prime is twice as big. Mn, M prime N prime is twice as big. Ml, M prime L prime is twice as big. And by the way, these are parallel. Parallel, parallel, and parallel. At least if compass construction was all that we cracked it up to be. So that's how we do this one. We're going to do it for the next few. And of course, it'll take a while. It's especially when I have to do this compass stuff the way that it is. All right, let's go to number 8. We're going to go from center P this time. So you're wondering when center P comes into play? Here it is. So number 8, center of P. And K equals 3. Let's go and change that to an 8. Let's paste a new diagram in here. I'm going to have to... Okay, it's already shrunk. And I do need it really to be shrunk once again because I need to go 3 times farther out, and I hope I have enough room all 3 directions. I cannot guarantee this for any sort of measure. Let's maybe shrink it just a little bit more. There we go. Hopefully this will be enough. So now I'm going to ignore center C. Center P is where it's at, all right? So let's once again draw lines outward from P through L. That's more than far enough. Way more than far enough. And M, this might be an issue with that line thing once again. Yeah, a little bit. I'm just going to have to deal with it. I'm going to have to call that what it is. I probably have to go farther out, though. Kind of like that. And then N, let's go as far out as I can. I think this will fit. I think this will fit just fine. The problem is this snap part. And maybe you're doing the same thing. You're like, okay, I don't have to pause your video as much because I'm drawing the same things, Mr. Robinson. You go, Mr. Robinson. All right, and I will. Let's go ahead and do what we did last time, only this time K is 3, and it's centered at P. So with K is 3, we have to do 3 of these now. Here's like one of them for L, right? 1, and now let's go on that one and do it again. 2, and then let's go on that one more time. 3. So that's the idea there. This is where my L prime will be located, 3 times farther out than the previous guy. And I really like the transformations for these. It definitely better explains what it... Listen, we can do it on graphs, but this better explains what it is you're doing and why it is that it works the way that it does. Especially when you choose different centers. These are not all at the origin, right? These are just at whatever they have. So 1, 2, 3 for N prime. Close enough. Especially because it snaps outward, so these will never be perfect. But there's my N prime. Let's see, can you see that? Not really. And M prime, I should say. Let's rotate that around, shrink it to fit. Sorry about that. 1, expand it to fit. As best as I can get, really. 1, 2, and 3. I could probably get that one little pixel farther out there. There we go, 3. All right, so this is my M prime. So it did fit by plenty. I got it. So enlarging from something that's inside the object is probably a better look at what it is that we're doing with it. You can probably see the parallel bits more, especially without any sort of overlap. So take a look at the new triangle L prime, M prime, N prime, enlarge from that center P like that. I mean, if I erased everything besides the blue, then you could really see what I was going for there. But that's 3 times the size. Once again, you can see parallel, you can see distances and all that jazz. There's number 8. Let's move forward. Number 9. K is 1/2 centered at M. Now, I'm glad it's centered at M personally, and I'm actually going to make this one bigger because we're reducing. We're going to 1/2 here. But it'll actually be helpful if you have a kind of a bigger version of this one. So number 9, center M, K is 1/2. So 1/2 does mean reduction. The reason why I like it at M is because this is something that was out of this section, the lecture itself. M and M prime are at the same place. If M is your center and I go half the distance closer to the center, then I'm still at that center. So M prime is where M is. There's nothing I can do, right? That's just what it is. That's good for me. It's one less thing to worry about. I can ignore P, I can ignore C, by the way. With the compass, though, here's the interesting part. Because, listen, could you guess and check? Sure. Like, I could go like, this is about half. Let's see if it worked out. And, oh, man, I just missed it. It wasn't, so let's shrink it and do it again. You could do that, but I think it's more of let's get it right, and let's get it right the first time. So in order to do this, to get midpoint with a compass, you can do perpendicular bisector. So I could do this here. Let me make it a little less notable. Make a big arc there. So what I'm doing is I'm basically finding L prime. I'm finding L prime right now. And I'm doing the perpendicular bisector thing. If you haven't done this with me before, then I'm not really going to speak too big on it. But I am finding the perpendicular bisector of L. And hopefully you can see these very faint lines that I'm doing in order to get this one done. So this is the perpendicular bisector of segment ML. And this is half the distance here to M to make L prime. Now, why am I doing a perpendicular bisector on this segment? No, not why am I doing a perpendicular bisector. That's to get a midpoint. By the way, I don't care about this line thing anymore other than just to have it. I'll just keep it. But why do I care about a perpendicular bisector of this segment? Because these are the lines that this is from. This is my center. My center to my point is on this line. Everything that I do is on this. This is where we expand and contract from. So MN, we're going to be going on that line as well, and we're going to do the exact same thing. So there's M prime to L prime. There's reduction, and that's midpoint. Let's do the same thing for N, for MN, etc. Maybe expand it a little bit more. And yeah, this will look a little confusing with all the things here. I don't need to keep them, but I will. Let's draw out another set. This is in green. Hopefully you can see that. Doing that pivot guy. And let's do it here on N. And do this other one. Right there. Hopefully you can see what's green. If not, here, let's make it a little bit darker and showy. The problem was when it kind of gets more in the way and you can't tell. Hopefully you can see it now. Now this green thin line, I'm going to do right there. It's going to be yet another perpendicular bisector. The only importance of this perpendicular bisector is that this is a midpoint. Half the distance from M to N. This makes this N prime. N prime. And I'm going to keep those on there just for reference. But, and I'll make this one thicker, this triangle thicker. This is triangle M prime, L prime, N prime when reduced with scale factor, or dilated with a scale factor of 1/2 as reduction centered at M. Centered at M. So that's what happens there at 1/2 as a reduction. And you still get things of instances of parallel and half the sizes and all that. This is a really good way to show what similarity is all about when we get into that in the previous sections here. All right, that is number 9. I have one more, at least for now, for transformations. I do not know if there are transformations beyond this one. These are the only 4 that I'm aware of that have transformations. So let's look at number 10. Number 10, 25%. Okay, this one's also a reduction. Actually, oh, no, there are 4 more. I'm sorry. 11 through 14 are also transformations. So we'll do it like we do. So center of C and K is at 25%. Now 25% also means 1/4. So I'm going to have to do this kind of thing twice. If you let me for a second, I'll be right back. And we're back. Okay. Let me just copy and paste this one from before here. Copy, paste. Because it is a reduction. This one is, it's gonna take some time. Now we are going from C, which means we got to do this several times as well. Okay. And the 1/4. I'm probably gonna have to erase portions along the way to really not make this look cluttered, because even if I understand it, I don't think you'll really understand what you're looking at anymore. So this time I do have to draw lines from C out to these. So that, guys, this is gonna be a long problem. Oh no, not this again. Okay, let me if you don't mind, I'm gonna rotate my objects a little bit. It's all the same to you because you have it on a piece of paper. So let me rotate it in such a way that this becomes a proper straight line. Let me just do it that way, and then I'll figure it out. Maybe I should have paused for this reason. Even the rotation snaps, which is really strange. I can't seem to do less than... Oh boy. I don't know, man. This is weird. Anyway, what are we going to do with this problem compared to the previous problems? I'll just do this. What are we going to do with this problem compared to the previous problems? How will it be different? 1/4 means we got to do a perpendicular bisector of a perpendicular bisector. So this will be 2 onto each other here. Now, the future problems, I don't believe there are any reductions that are like 1/3 and something like that, because you might ask, how do I do 1/3? That's kind of difficult to talk about, right? Because unless you're doing guess and check, a midpoint of a midpoint of a midpoint, that goes to a 1/4 and an 1/8 and a 1/16, and those aren't multiples of 3. So how do you do it? You wouldn't really, outside of guess and check. That's why they wouldn't do it to you. That's why they're not doing it here. But here we are doing something where, I'll just keep it like that. A 1/4 is half of a half. So I need to do perpendicular bisectors. Here, I'll make it as unobtrusive as possible. That's right in the way of everything. I'm not going to make it unobtrusive. I'm just going to do what I'm going to do, and I'm going to have to erase parts as I go. So here, I'm going to first find the perpendicular bisector of CL, and this will only be half the distance away to begin with. Okay, so this guy right here, that dividing line gives you the midpoint from C to L. Let's kind of just mark that off with this right there. That is not the point of our thing, though, because now we got to do half of that half. Half of that half. So now let's get rid of those. Let's just boom, boom, boom. Otherwise, like I said, this will be a huge clutter because that's only one set of lines. Just imagine all the other ones along the way. So let's do another set here. Don't worry, once I get it all done and drawn, then I can move it. Whoa, I didn't want to move that. I want to move my compass. So let's do this one as well. So here's half of a half, or a 1/4. And this is where L prime now sits. L prime. To make sense of it before I do some other ones, here's essentially what we did. It takes 4 of these, and this will not be perfectly to scale because the way my thing snaps around, like, see, that doesn't even either undershoot it or I kind of overshoot it. But it takes 4 of these, 1, 2, right? And sorry, this 3 and 4 to get to there. Of course, they're kind of slightly overshot just because how it works. It takes 4 of those to get to there. That's how that 1/4 works because we reduced it. Okay, so there's L prime. Now I can get rid of that, and I'm going to get rid of everything that's not just that individual point. Otherwise, like I said, bunch of clutter. And I have to do this 3 times because C is not one of the points that this thing's projected on. Let's do it from C to N. This one I'm going to expand as far out as I can. Just did the splits with my compass. And I know you can't see the bottom where it intersects with the top. Just go with me on it. Drawing a line all the way down through it. I made a perpendicular bisector from C to N. Basically, this guy is perpendicular, but more importantly, it's a midpoint. It's a midpoint right here, but I need to get the midpoint of that midpoint with C. So let's get rid of those. Probably didn't need to do full splits. Okay, let's do it again and shrink the splits. And from C to that point, once again, find the intersection of your arcs here. And you don't need to do big arcs. It's just easier for my tool that I don't have to keep clicking this green button while going along. It's just a lot faster this way for me. So here we go for a second set. Like that. And then this is the midpoint of that midpoint. So this is the official point that we're talking about. This is our N prime. That's our N prime right there. Quarter of the distance away from C. Now let's do M prime, which would kind of be the hardest one just because it's so small. I like bigger ones more because of what I can kind of do with them. So I'm past halfway. Let's do that, and let's do this. This is, remember, only the first one. So where do those intersect? Boom, boom. Let's draw a line through these. Now, this compass stuff is through knowledge of what we did back in Chapter 6. If you haven't done it with me or you haven't done it with your teacher or whatever, you might be a little lost. Excuse me, and specifically what we're doing with these things. But they're used to gather midpoints. So I got that one. Now let's do one more. The midpoint of the midpoint, if you will. And C. So just a little bit smaller. I'm proud of my work so far on this one. Long as it may take, ultimately. And of course, as many snap things, this won't ever be perfect. But deal with it where you can. And this guy, this is my M prime. Okay, so now we'll connect those dots. Once I get rid of all this, let's even get rid of that guy and that guy. All right, now we get to connect these dots. Not C, but L prime, N prime, and M prime. And this is a reduced triangle. Best as I can kind of do there. That's a reduced triangle compared to your original. Okay. A quarter the size. A quarter the distance closer to C, or whatever, whichever way you want to say it. A quarter the distance from C. All right, that's number 10. Now as we move forward, there are 4 more compass construction ones. Why? Sadists, I tell ya. Hopefully from C to S is a horizontal line, and I don't have much trouble with this. Now this is a K value of 3. I do have a 0.25 and I do have a 0.75. So listen, it's going to take a while. If you don't have these problems on your problem set, then skip on by and find number 15, etc. in the timestamps or whatever comes next for you, because this is probably going to take like the next half hour. Center from C. Okay, center from C to K value of 3. I need to make it pretty big here. 1, 2, 3. Or I need to make this pretty small because it's about to get pretty big. It's probably going to run into what I'm about to write here. So center of C and K equals 3. So let's see. I'm really curious immediately, otherwise it'll mess it up. From C to S, if that is a horizontal line. You know what? It is. I mean, even if it's not, it is, right? It's close enough there. Let's do a couple more of these. From C through R. Okay, it won't run into my writing, but it will snap away. And then C to U. Really expand these out because 3 times farther. I don't know if I'm going to reach 3 times farther out properly with this. C to U and then C to T. Oh yeah, let's go. Okay. Okay. All right, let's get our compass. Let's go to work. We're going to do 3 times farther out. What does that look like? Well, can I flip this? There we go. Let's measure out C to R. Whoops, about like that. Good enough. So that's one distance, right? And then 2 distances. Ooh, I do need to make this a little farther, I think. There's 2 distances, and now 3 distances is going to look like that. Okay, so R prime is all the way out there. all the way out there like that. 3 times farther out. S, not quite as far out. Let's shrink that guy. Unfortunately, I don't think I can get the right snappage with my compass. Whatever. S, that's 1, 2. Go a little farther out than the thing. 3. That'll have to do. You can be perfect on your paper. S prime. Let's go to T. Might be on the same curve. Nope. 1 snap out. Yeah. All right. So there's 1. And 2. Shoot. I don't know if I can get it perfect. 2. And then 3. Like there. T prime. T time. And then U. I don't know if I made that one far out enough either. Let's expand it before I regret not doing it earlier. U. That's a little farther out, but I think if I snap it inward, it's going to be too close. It's one of those tweeners. Let me get this back closer to C, go 1 farther out again, and say that's good enough. So 1, 2, and not quite visible. Not quite visible. I'm still going to draw what I can. Well, I don't know how to draw what I can. It's off the map a little bit. Let's just take everything and move it just a little bit. Oh, this is locked. Hold on. Okay, hopefully you can still just identify where that C kind of is. So 1, 2, and 3. It's literally on the edge right there. So, like that. Best I could do with that. And that's going to be U. U prime. Okay. It's a solution guide video. I gotta make the solution guide. And changing colors for the tool. Okay, here we go. S prime, R prime, U prime, and T prime. There we go. 3 times bigger than the original guy that we have there. I'd like to erase everything else, but you know what? I'm just going to leave it as is. So there is from center C, and that's one problem there. That's why I said keep moving on if you're not doing these problems. Number 12, probably a little better off from the inside, growing out twice as far. Center P and K equals 2. Number 12. Center P and K equals 2. Okay, also an enlargement. Whoa, not that kind of enlargement. How about like that? Wait, how about like that? It's fine. Drew a little something. Whoopsie. All right. Let's do straight lines outward from P. From P, oh, smaller lines, of course. All right, from P through S. Look at that snap. Every time I let go, you probably wonder why that happens. I don't know. It's the technology of the software. It's the software. And then I try and account for the snap, and that time it did not snap whatsoever. It's like Thanos, man. Account for the snap. Oh, it did a light snap there. I think it goes more extreme as you go in a certain direction. And in my 12 years of doing this, I've never yet learned it. See, that one snapped upward. Don't know why. Don't know why. All right. Of course, I didn't make the software. I can't blame them if it's a technicality that you just can't overcome. Okay, let's go twice as far. So 1 length, 2 length. Let's just draw the arcs first, then I'll do the pen stuff after. 1 length, 2 length, red length, blue length. Well, actually, that's not bad. 1 and 2. Okay. For T, Is that good enough? I guess so. 1, yeah, totally. 1 and 2, and for S. Let me change it this other direction so you can see it on top. For S, one more snappy snap. Nah, the other one's going to be a little better, but still not great. 1, I'll just go farther out to compensate. 2, okay. So let's plot those points. We got R prime, U prime. Where's Optimus prime? T prime, and S prime. Once again, you'll really see the aspect of parallel lines and such, especially from coming from a center such as this one. Oh, this is one I can't really snap perfectly. We'll just go with it horizontal. It's supposed to probably be a horizontal line anyway, so if something wasn't perfectly to scale, then just, again, go with it. Not a 1, excuse me. I'm trying to move this up. Okay, pretend like it was there. And then S prime to T prime. Excuse me. Okay, so there is that one. You can see the enlargement twice as far away and twice as big. All right, 2 more. These ones are reductions, and they have those weird decimal or percentage amounts. Let's take a look at number 13. So on number 13, center is R, which is a good thing for me. I have 1 less one to deal with. So center R. And K is 0.25. How long has my video already been? Only on problem 13. Not quite an hour, but by the end of these 2, it will have been past an hour. That I will have ensured, which is just crazy. Thank goodness there are no proof things, and I was aware constructions would happen, but man, this really... Okay, I don't really need C, so I'm going to expand this as far out as I can and use that. Now remember, the center's R, which means the only line I really need to draw is the one from R to T, because from R to S is already drawn, and we are reducing, not enlarging. So I do need to draw one from R to T. I can ignore P outright. I don't need it. Now the 0.25 we've done before. We have to do midpoints of midpoints. So let's get our compass. Let's go to work. Let's start with S. Midpoints of midpoints. And... or bisectors of bisectors. So 1, and on the other side 2. I'm just going to go whoop-de-doop because I'm going to erase it anyway. So as long as I have something more than halfway and I draw a line that I feel kind of comfortable with, which that is not one yet, as long as I draw a line I'm kind of comfortable with, then I'm good for bisector purposes. All right, that's pretty good. So here's a midpoint. Now 0.25 is getting that much closer, so boom, there's 1. Now let's erase those and go to the next set. Let me lock this in place. Okay, let's do it again. From here, oh, too far. Shrink it. So 1 and 2. Boom, boom. I want it to snap correctly for me. Snap properly, please. I think once I create the initial thing, then it snaps just fine for me. So there is my official S prime. By the way, R prime is where R is. I can do that right now. R prime is where R currently is. Okay. All right. There's the first one. Let's go to T. Let's go beyond on this guy. Now I'm very happy that this one only needs 3 points. I think the last one has to use all 4, so I have to really work on that one. Can you see that? It's probably hard to see, huh? Let's make it a little easier to look at. So there's that one, and T. Okay, here's our halfway. About right there. Okay, let's do another set. I don't really have much to say at this point. I hope it's okay that there's a little less downtime. Or a little less talky talk, you're like, so there is a God. Mr. Robinson's not talking, but he still is. He's saying words. Oh. There we go. Should have erased the other set beforehand. Okay, I'll go with it. There's my T prime. Okay. Let's erase all that. Imagine if I still had all these arcs, because you might have all the arcs. And listen, do everything light enough so that you don't need to erase, really, but then you can keep everything that you can. All right, now let's go R prime to U prime. Or R to U, I should say. Well, R prime to U prime, we're going to come up with it. Let's start with this. I'll just keep this one dark. And sick of changing all the opacities all the time. Oh, okay, well, it's going to make it tight, but you know what? It doesn't change the fact that the midpoint is right in the middle. If this were, honestly, here's the thing. Getting closer to midpoint like this is probably better for what it's probably more accurate. Perpendicular bisector, on the other hand, probably wouldn't be as accurate if I did it this way. I would probably want it to be farther out than that, but closer to midpoint is probably better for what you do there. I'm more assured that I'm at that midpoint, I feel. Except for the pixelation of my stuff. The way that the pixels work on these and the way that they snap. Probably not perfect. Never was meant to be. It's just meant to guide you, though, right? So this one being farther out, probably less accurate. But you know what? The idea's in place. Perpendicular bisectors. And I can't say that I didn't try and do the work here. So U prime is there. Okay. So now let's make this quadrilateral. This reduced size quadrilateral. R prime is still where it was to begin with. So we're going to go from here to S prime. S prime to T prime. T prime to U prime. U prime to R prime. Which, of course, like I said, this is supposed to be kind of a horizontal line here. So looking pretty good. Okay, that's a quarter of the size. And it has that similarity approach. So it's like it's growing or shrinking from there, which is nice. You know what I could probably even do? Let me try this. I don't know if the object will let me do it the right way, but if I group it, if I expand it, oh, never mind. Okay, but look, I can grow it basically to that, right? It's not perfect because the way I made things, but that's kind of cool that you can see things that way. I probably could have done it with the other objects, but I thought about doing it because of where it was centered at. And the last one, hopefully the last transformation overall, number 14, center C and K at 75%. Center of C and K equals 75%. Boom, boom. Now the center's at C. So this time I do not get the luxury of being able to just do it 3 times. I have to do it all 4 times here. I have to draw 4 different lines. Okay. And now 75%. I will do a midpoint of a midpoint, but this time it's going to be toward the pre-image, not toward the center. So while I start with, you know, the ones from the center to the thing and all that jazz, the next one is going to be toward the pre-image, not toward the center. But it is still midpoint of a midpoint. That's not going to change there. 75%, by the way, I should just make mention, 0.75 is 3/4. 3/4. So 3/4 of the way from C, rather. So I got to do this 4 times, which means 8 times, because I got to do a midpoint of a midpoint, is the way that I say that. Let's just keep it dark as we go. And I'm going to try and get as close to midpoint as possible with some of these things. Like, that's too short. Yeah, that's probably a little far, but that's okay. So first set, intersect there. You know, I'll just eyeball it. Boom. Okay, for the second set, and I kept saying it, instead of going between this midpoint and C, I'm going to go between this midpoint and R. That'll make it 75%, 3/4 of the way. My quadrilateral will be 3/4 the size instead of 1/4 the size, if that makes sense. So that's probably just under midpoint. Let's go just past it. Like I said, since we're not officially doing perpendicular bisectors, and we're doing more midpoint, it's okay to get it close to midpoint and stuff, because I won't need the line in the end. Ooh. Oh, okay. Like, okay, for example, this one helps me understand that it's probably about right there. I'm not going to draw the extra line in between because it's close enough. So that's the one that I officially need. That is my R prime. That is my R prime. So I don't need any of these. I just need that 3/4 outward from C there. Okay, let's do it with S. Like I said, closer to midpoint is probably better for me. So there, let's just get the roundabout. Yeah, it's about right there. The closer I am, the better I can approximate that. It doesn't matter, because once I draw my point, it's somewhere on that big blob of a point that I made. Okay, now let's kind of get closer to this at midpoint. You can tell I'm a little impatient with these kinds of problems now. Look, I've done them, okay? I've done my share. Have you had to do this many? Maybe, I don't know. So it's going to be kind of right in the middle of those two. As long as I'm close enough to midpoint, I can venture a guess I'm going to. About right there. All right, so that is my S prime. And again, generally I would draw a line between, but I think that's where it would hit when it comes to the line itself. That's my S prime. It is a reduction. Let's go to U. This one a little farther out. See, I couldn't reach the full width like that. But let's not go that far either. Let's go to kind of, yeah. Let's see if that was enough. Whoa, I just duplicated this over here. That was very unintentional. Very unintentional. See, this is really, it's really bizarre to do on here. You've probably understood. Oh, shoot. I didn't keep the size the same. What was the size? Ooh, I don't know. I guess it was 190. I don't know what the size was. So I forgot I have to keep the size. So 190 and 190. I'm sure I haven't done that before. Oh, look at this. I fell short of the midpoint, but you know what? It's still halfway in between these. So why not? So is this a little trial and error? Sort of. I mean, it's going to be in between those. I'm not wrong. Might as well just fill the gap and just pretend like my pivot's going to land on there best as it can. And remember, I'm going to go from the midpoint to U, not to C. This time I'm going to be a little more accurate with it. I can't do that twice. So here and here. If you're really lucky, you'll pretty much be at the midpoint itself. Look at that. But like I said, that's not trial and error. Trial and error means repeating it over and over again. I just did it once, and that's just working out, I think, in my favor there. All right, that is U prime. And then lastly, T prime. Let's do that one more time. Midpoint in between these guys here. Okay. Let's actually draw the line this time. Perpendicular bisector creates a midpoint. It's not yet T prime. We've got to do it one more time. Let's get rid of those. Get them out of the way. Is this exciting? It's a brand new video. Is it an exciting video? Oh yeah. Compasses. Let's go. Let's go. All right, that's a little far out. There we go. Wee. I'll make it exciting by saying wee. Wee. See, even if I draw the line, not only will the line probably snap differently like that, and it makes it inaccurate, I probably could have just been more accurate just by doing my thing. But I did have to get closer to that. Boom, like that. That's going to work out. I got T prime. Hopefully that was my last compass construction. Never know. You will see me visibly upset if I have more compass construction things to do than these. All right, so let's just delete the compass and assuming that that's it. Happily so. Okay, so let's connect all those. This is 75% of what it was before. 3/4 the size. So not 1/4, but 3/4. So compare that difference there to that one there, right? Completely different. Okay, that is number 14, and y'all, that is some transformation or some construction stuff on dilations. Now we're going to do them on graphs, which is generally more where you would see them. And I know I have some lecture things with examples on dilations in this way of old. In exercises 15 to 18, graph the polygon and its image after a dilation with scale factor k. And these may be the problems where you will have items that are that I need a bigger scale for. So let me write these out to begin with. X is at 6, -1. Y, because here's what I want to do. Y is at -2, -4. I'm going to come up with what the things are first, if that makes sense. K equals 3, by the way. Let me do this up top. K equals 3. So let's triple these values. This is what you do. For x prime, I'm going to triple 6 and get 18. This is an example of how I need more stuff and more room. -1 times 3 is -3. Y prime, maybe a little more room. -6, -12 as we triple those. And then z prime, don't really need it as much, but why not? What the heck? Z prime at 3, 6. Okay, let me get my graph paper stuff. And I guess I just need to change the scales. And I hope you're okay with that kind of thing, because it's very uncommon to find graph axes online or to use like a Photoshop version of something where I can totally make this happen in a more efficient manner. Next time I'll make sure to get these on the same shot together for this problem. So x, y, and z. Oh, first of all, I'm going to change these to like 20 and 10. I'm going to go by 2s because I need to reach 18. So -10 and -20, like that. So now all of these go by 2s, not by 1s. Keep that in mind when we do these. This is one reason I wanted to write them down. The other reason is to get the transformations by multiplying by 3. So we'll go x, y, z at, remember 6 is now here. Here's 6, -1 for x. Y is -2, -4, and z is at 1, 2. So remember they are going by 2s. So z, x, and y. Now everything's going to be tripled in size. Let's first connect those. I'll make the other one a different color. I guess I'll make it red. I'll do the same thing that they do on the problems when they do a transformation. X prime, y prime, z prime is in red. We'll go 18, -3, like this. And y prime is at -6, 2, 4, 6, -12. Yeah, scaling by 2s ain't a problem. Z prime is at 3, 6. Maybe scaling by other things will be a problem. But 2s, nah. So there's Z prime. I might use a different version of red next time, though. I don't like the way that it kind of bounces off the white for me. It's kind of hard to look at, and if it is for you, I apologize. So notice how this YZ segment, they're on the same line there. Kind of neat. But that's the graph with that scale factor for number 15. Okay, number 16. And like I said, this time I want to give myself more room to fit the graph on the same portion as what I write after transformations. So I'll shrink it, sure, but I do want to fit it properly here as well. So number 16, K is 120%. So 120% is the same thing as 1.2, but it's also the same thing as 6/5. Now that's something you'd have to dive into a little more to make sense of. It's also 120 over 100. You could reduce that. 12 over 10, you could reduce that. A lot of different ways you could put it. If you got to use a calculator, you can multiply 1.2, etc. So A, B, and C. I'll be honest, I'm going to keep the scale the same. I know one of these is going to turn just a little bit bigger, but it's not much bigger. So A prime, 0 is still 0. What's 5 times 1.2? 120% more than 5. Do the 6/5. Divided by 5 is 1, times 6 is 6. If you divide it by 5 first, it'll make it a lot easier. -10 divided by 5 is -2, times 6 is -12, and this one is -6 right here. So the other one was positive 6, and this is a positive 6, negative 6. Like so. So the negative 12 is a little bit out of reach, but not really a problem. So A is at 0, 5. B is at negative 10, negative 5. This isn't going to be much bigger than it was. 120%, 1.2 times bigger, not much. C is at 6, negative 6. So here's my IBC. It's going to get in the way of my next thing. Maybe I can write it on the inside. ABC. And like I said, I'll have a different shade of red for this next one, just a much darker red. I didn't have to use red, by the way. So ABC. A prime, B prime, C prime, just 120% bigger, just a little bit. We're going to look at, let's do this color red. A prime is right here. It's not really red. B prime is at negative 12, 11, 12, and negative 6. So you're kind of like that. Why not? And C prime is at 6, negative 6. Oh, I'm sorry. C was at 5, negative 5. I didn't notice what I did here. You probably were calling me out on this. Mr. Robinson, what are you doing? 5, negative 5, and then C prime is at 6, negative 6. Okay. So 6, negative 6 being right here. C prime. Got it. I corrected myself. No worries. So these will run parallel. Maybe they don't intersect or whatever, but they'll run parallel to each other. And you'll get the gist of, was that decent enough? Sure, of course. Look at that. All right, there's number 16. That was also an enlargement. The first two were enlargements, right? The next two are going to be some form of reduction. Now, 2/3 isn't likely one we would have seen in compass construction, but we are fine doing here when it comes to numbers, especially if the numbers are divisible by 3, which it seems like these are. And these are quadrilaterals. So on number 17, we have T. Oh, let me start with K. We have a K of 2/3, which I'll leave as that. Not like 0.67 or something like that. T is 9, negative 3. So to T prime, I'm going straight into it. T prime, 2/3 of 9 is 6. 2/3 of negative 3 is negative 2. U goes from 6, 0 to 4, 0, which is U prime. V, 3, 9. 2/3 of those are 2 and 6. And W, 0, 0. Well, it stays as 0, 0, which is kind of the point of dilating from center, from the origin. A point that's on the origin stays at the origin. Newton's first law of dilation. All right. T, boom, U, and I got to read the proper ones here, boom, V, 3, 9, some kind of quadrilateral, isn't it? W, oh, this is a convex quadrilateral, okay. Now it is a reduction, so we are expecting to get smaller, but, excuse me, it's a concave quadrilateral, not convex. This thing angles inward like that. So we're going to see things shrink into that. But remember, W prime is at the same exact place. So W prime is also right there. That's not going to change. U is at, or U prime is at 4, 0. V prime is at 2, 6. And once again, it's going to be on this line. If W is the center with W prime, things are going to be on that line, which is nice. T is at 6, negative 2. Kind of confirms, or T prime, kind of confirms that you got things right when you did it. If you did it right. So there are these guys here when I connect the dots. And there you have it. Right? So that is the reduction of these ones here. Seems accurate to me. Hope you guys got the same. All right, and number 18, another reduction. It says 0.25. We've seen that before from the construction ones. 0.25 is also 1/4, which means we're dividing our numbers by 4. So as long as they stay pretty accurate, we'll be good. J is at 4, 0. That means J prime is at 1, 0. Dividing by 4. K is at negative 8, 4. Whoopsie. So K prime is at negative 2, 1. L is at 0, -4, so L prime. El primo is at 0, -1, and M was at 12, 8. 12's a little out of reach, but in the same way, it's not unfathomable from what we saw before. I'll leave it. That's 3, -2. So let's go ahead and get those ones in. Yeah, these problems take a little bit to do. Only on number 18 of 50 something, so still have a ways to go here. And these are the easier problems. See, dilation, man, there aren't quick ways to do a lot of dilation. Oh, the first problems were pretty fast. So 4, 0, -8, 4. 0, -4. And 12, -8. 11, 12. It's really going to be pushing toward the edge of the screen there. So that's M. This was L. And K and J. Kind of parallelogram-esque. I don't know if it is one. Or rhombus-esque even. I don't know if it's one. They're not asking. They are asking for you to reduce it, though, and we're going to plot those points. We already got the numbers. We just got to plot them. JKLM. I don't know, that very well could be a rhombus. In fact, slope of +1. No, not a rhombus. It could be a parallelogram, though. Could be a parallelogram. They could bisect each other. L prime, etc. Let's do those. 0, -1. L prime. K prime is at -2, 1. M prime is at 3, -2. And J prime is at 1, 0. Okay. And yes, it's important that you label your points. Very, very important that you label your points there. Yeah, I'm convinced this is a parallelogram. Both of them, of course, are. Because angles are preserved. If opposite angles were congruent, they stay congruent. By golly. And yes, remember, it's not, you don't say, wait, why isn't this right? See, look, hold on. You don't take this object and say, and I'm not going to be able to move every part. You don't take this object and say, why isn't this object right in the middle of this right here? It's centered at the origin. It's dilating to and from the origin. This is the center. Things cast out from there, right? So the thing we did with compasses before, if you followed along and did those, they go from the origin out to here, from the origin out to here, from the origin out to here, from the origin out to here. Now my M isn't perfectly set because 12 is probably a little farther out, but I kind of ran out of screen room. Okay, that was those ones. We got 4 more graphing ones to do. You can notice these K's are now negative numbers. It's really not, I mean, listen, the calculation is all that you really do. There's nothing hard about that or easy about that. These will look different, but follow the points that you plot, and we can confirm that they work as they will, but they're not going to be inside the object in the same kind of way. You're going to see a bit of a rotation. If you saw any of the example ones we did earlier, then you'll know what I mean. So the K value here is -1/5. -1/5, which means we divide the numbers by 5, but we also change the sign of whatever they were. Whatever the sign was, we change it. So we are going to have a B value of -5, -10, and divide those by -5, and B prime is going to be at 1, 2, +1, +2. C is at -10, 15. You can see that that's a little farther out. That'll be important for us to probably change some scale things up. Now, +2, -3 as we change the signs. And D was at 0, 5. So now D prime is going to be at 0, -1. There's something wrong. If you see that happening, there's something wrong. It's glitching on me a little bit. That's happened to me in the past. Probably because I'm doing encodings while this is happening. I hope it's not making my video choppy. If it is, I really apologize. I don't want that to be affecting the video that we make together here, because otherwise it's like, uh-oh, I made an entire video with an entire amount of chop, and there's no way I'd want to redo this thing. It's like 3 hours long. So I'm encoding other videos while I'm doing this. Other videos I recorded. This is my 3rd video I'm recording today, by the way. My 3rd math video, so I'm taking advantage of the time that I have to do this so I can get some other stuff done. I'm traveling out of state this weekend. All right, so D is here. Oh, hold on. Let's change the scale. Let's go by 2s again because that 15. I know it's just one thing to change, but yeah, this thing is glitching on my writing here. I'm noticing it more and more here. sometimes it's not cooperating with me. And all I mean is that sometimes it doesn't write exactly where I have it right, and so the curve kind of gets messed up. So if it's going to happen a lot when I have to actually write some big things, sorry. All I hope is it's not affecting my video. I hope we're smooth. I hope we're good. Okay. D is at 0, 5. Now 0, 5 is right here. C is at negative 10, 15. Now that's right there. That can actually fit. C and D. Where's B? 1, 2. Where should I put this? Right here, I guess. B is at 1, 2. This is a weird looking shape. Hope it's the right looking shape. B, C, D. And we're going to negative 1/5 it. Oh boy. Oh, I'm sorry. B isn't at 1, 2. That's B prime. B is at negative 5, negative 10. That makes more sense. Okay. Yeah, I should, normally I'd plot these points first and then do the calculations, which makes it easier to not make a mistake. But because I wanted to see my scales of things, ultimately I did do it this way, so whatever. All right, B prime is at 1, 2. We'll talk about how this thing works in general. C prime is at 2, negative 3. Remember, these are going by 2s. And D prime is at 0, negative 1. B prime, C prime, D prime. Okay. Yeah, smaller, yeah. And I did go by 2s. Okay, so how does this work as a reduction? Well, the center is still at the origin, but it inverts through the origin and out the other side. So I can draw a straight line from C to Z prime, and it goes through the origin there. From D to D prime, it goes through the origin, and B to B prime, it goes through the origin. So it's not the perfect example of one to see exactly what's going on. I think you'll see another image of one that does work out. But this does go as intended. It kind of has a camera obscura effect. It is a reduction. And yeah, we did it correctly. We did not do it incorrectly. All was good. All right, number 20. L is at the origin, and we're centered at the origin, so that all works out. Oh, K, by the way, is negative 3. K equals negative 3. L is at the origin. M is not at the origin. N is negative 3, negative 6. Yeah, we're going to have to double these again because of that. So negative 3. Thanks, N. L prime still at the origin. M prime is at positive 12, negative 3, multiplying by the negative 3. And N prime is at positive 9, positive 18. You know what I could do with this one? I have this tall graph, and I can attach it for you online. I have the tall graph. I can work this one, and I think it'll serve me better so I don't have to scale by 2s. 17 is the top, 18 is one above the top, and 12 is not so far away from 10 still, in the same way as it was before. So I'll attach both of these. You can just use this one, please, just so I don't have to scale by 2s again. Maybe it'll help us better serve what we're doing. So L, 0, 0, M, negative 4, 1, N, negative 3, negative 6 is the original triangle. L, M, N. Hold on, change my color and shape and style. Let's do that again. No, it just snapped again anyway. Arrgh. Alright. Alright, that'll work. L prime is on the same point. Now it's going to kind of flip. M is at 12. Here's 10, I think it was 6, 7, 8, 9, 10, 11, 12. Sure. And negative 3. So it's a little off. That's okay. M prime and N prime is at 9, 18. So 9's up here. 17, 18 is up here. So with the taller graph paper, it works. It works. And let's connect those ones. So you can clearly see this time where the line, I mean, the line's all cast out from L, right? L is the center. And you can kind of see that inversion. N goes from here through the origin and out the other side is N prime. M and M prime, if things were perfectly drawn, what it should be, it would be a straight line. L and L prime is right there. And it works just fine. All right, that's number 20. Number 21. 21. Quadrilateral. K is -4, and you can see this -7 that's going to be multiplied by -4. So this one, clearly, we're going to have to just change scales. We'll go based on the old kind of graph. So R is at -7, -1, and R prime, therefore, will be at, see, why isn't that curve working? 28, 4, both positive. S, of course, they always put a 5 near an S, so I have to really make one look different. And S prime, also multiplying by -4, -8, -20. Oh, yeah. Big stuff. T is at 812. Oh, sorry. T prime's at 812. T is at -2, -3. T prime is at 812. And U at -3, -3, and U prime. Here's my concern with this one. We have to go to 28, which is pretty far off from the thing. 12, 12. Pretty far off from the thing. I could go by multiples of 3, but then it's going to be weird to put these even numbers or numbers that aren't multiple of 3 in their place. And that's pretty much everything. That's even 28 is not a multiple of 3. I could go by 4s. You know what? I could go by 4s. All of these are multiples of 4. Let's do that. Let's go by 4s. Multiples of 3 would be really awkward, and 2 would not be big enough. Let's bring that up a little bit. Okay. So going by 4s, that makes this 20 and this 40. And I believe everything is a multiple of 4, which means I can go right on increments. So this actually doesn't end up being bad, ultimately. So, oh, these aren't, though. I forgot. All right. Oh, well. R is at negative, so -7, -1. So remember, these go by 4s. 4, 8. So -7 is a quarter, 3/4 of the way. Basically like a dilation thing. So like right there. This will be a little tough. That's R. S is at 2, 5. 2 is half of 4. 5 is 1 1/4 up from 4. So like that. T is at -2, -3. Hopefully you can trust what I'm doing with that. About 3/4 of the way down. And U is at -3. -3, -3? Oh my goodness. They're going to be right next to each other. Well, I'm not going to use the line tool for these. I'm just going to pretend like I know what I'm doing. R, S, T, U. All right. Well, the bigger version will show me what it is that we really have here. So on this bigger, let me change that U. That doesn't look good. That's a little close there. All right. You know, if they were just better at not giving you problems like that or providing you graph paper, that would work. All right. R is 28, 4, 20, 24, 28, and 4. That's R prime, I should say. S prime is -8, -4, -8, -20. We'll just take our word for it that we did the math right. T prime is at 8, 12, 4, 8, 12. And U prime is at 12, 12. So 12, 12 like that. There's a little more separation. When it's 4 times bigger, you can see a little bit more separation, which is just nice. I love it. Let's connect them dots. So we'll use the line tool. And even here, it's hard to use the line tool on those two. Okay. I think you can see the thing for what it is. It's flipped and enlarged. By flipped, I mean rotated. Yeah, that's the best as I can do for that with this kind of scale. I was aware that something like that would happen, and there it was. All right, last one, number 22. And then maybe a little less on the graphing front or the compass construction front. My hand's kind of hurting from all this. All right, K is -0.5. I think we can all agree is -1/2. And sorry if the handwriting's weird. Once again, something's glitching with my encoding. Can't control that. Cannot control that unless I choose to not encode, in which case you won't get videos up sooner. So if you want them up, I don't have to deal. Let's just hope this video's not choppy. Please hope this video's not choppy. All right, W is at 8, -2. See, it's not registering the hit. 8, -2. I think it's getting worse. That's the problem. W prime. Oh, no. Oh, no. I just got to write with more deliberation. W prime is at -4, -1. Oh, +1. -4, +1. When dividing by -2. X is at 6, 0. And X prime by -2 is -3, 0. No, I wrote a 0. Y is at -6, 4. Boy, this is a problem. Y prime is at divided by -2, 3, -2. Z is at -2, -2. -2, 2. Sorry, I'm getting bothered by the fact that this is happening and going to happen. I'm gonna have to keep apologizing for things that don't register properly when I do this. I have something that's doing another hour 45 of encoding. Maybe we'll still be doing the video during that time, and then by the end all will be right. So it's weird though because I'm doing on different drives. I guess just working itself. Okay, all those fit? Yeah, all these fit just fine. I should have assigned this problem to my students. 8, -2 is W. 6, 0 is X. -6, 4 is Y. -2, 2 is Z. Are we sure that was right? 8, -2, 6, 0, -6, 4, -2, 2. This is a strange looking graph. Maybe I shouldn't have signed it for my students. That was the original. And we're about to reduce it. Not quite a parallelogram. Close. But not quite. This thing kind of offsets it right there. So X, W, Y. All right, now reduce with the negatives and all that jazz. So now we got -4, 1. Oh, that's going to be right where Z is here. So -4, 1 is W prime. X prime is -3, 0. W prime, X prime. Y prime is 3, -2. And Z prime is 1, -1. Okay, then I trust my original one was right, because this is just as weird and a smaller version of weird, which is harder to work with. Oh, see, I didn't do that. Yeah, wow. Okay. All right, guys. So that is those sets of problems. Let's keep moving forward and see what goes beyond this, because I actually don't know. Okay, error analysis in 23 and 24. Describe and correct the error in finding the scale factor of the dilation. You know, we go from P to P prime from blue to red, so this should be a reduction of some sort. Therefore, the K value should be less than 1. They obtained a K value greater than 1, but K should be between 0 and 1 because this is a reduction. Basically, they divided the wrong way. So let's fix that. The K value should not be 12 over 3, but 3 over 12. K is 3 over 12, which is 1/4, not 4 over 1. Sorry, I'm going to keep apologizing, but this thing is not registering some of my hits. Number 24. You'll be able to tell when I'm trying to write something and the writing looks really off. Not like my usual bad handwriting, but something that's just not actually registering. You'll know what I mean. Number 24. It's just the opposite effect here. Now, what you can tell here is you go from 1 to 2, from -2 to -4, and from 1 to 2 there. Everything's clearly being doubled. So once again, it's the opposite effect. They obtained a K value, but K is greater than 1. It's just the opposite of what I say here, because this is an enlargement. Once again, they divided the wrong way. Now, you don't even see... Oh, no, they do show division. They did 2 divided by 4. Oh, I didn't see that 4 and that 2. Now, there's nothing wrong with the idea of what they divided, the 2 and the 4. They do correspond as parts, but you got to do 4 divided by 2. So very unoriginal set of two different error analyses. I know one's a graph and one wasn't, but it was just the same kind of issue, only reversed. All right, in 25 to 28, a red figure is the image of the blue figure after dilation with center C. Find the scale factor of the dilation, then find the value of the variable. So it's almost a proportion thing, if you will, to find the value of the variable. And because we have to find a scale factor, maybe I don't get to play with it that way. Maybe I do. It depends on the problem. But yeah, it's just based on the growth and all the stuff. So the red is the image of the blue. That means we go from blue to red. That makes the first one n enlargement, for example. So if I want to find k, I want to find parts that correspond and divide them. The 15 corresponds with the 9. I get to do 15 divided by 9, and that reduces to 5/3. So if my k value is 5/3 for my scale factor, I can find my x by doing the same kind of thing. Now, x is the distance from center to blue, and then 35 is the distance from center to red. So ideally, it's like this. I'm taking my x value and multiplying it by my scale factor, and I'm getting 35 as a result. So how do I solve for x here? I can divide both sides by 5/3, which is also multiply both sides by 3/5, like that. And 35 divided by 5 is 7 times 3 is 21. That is the value of x. That's one way of going about this problem. It is 3/5 of 35 given that the scale factor is 5/3. I know that can sound very confusing with what happened, but keep in mind how this thing works when it comes to enlargements and such. Maybe those numbers weren't quite as good. This next set hopefully will be a lot better for you to make sense of what the heck we just did. And then maybe on the last two, I'll set them up as actual proportions. It is something that will be necessary and relevant for this chapter. Number 26, we're going from blue to red again. Once again, an enlargement from 14 to 28 is 2. 28 divided by 14, that is the scale factor. So n is the variable. I take n and multiply it by 2. I'll put the 2 in front this time. N times some 2 is 12. What is the n value? I think this is one we can all agree. Divide both sides by 2, we get n equals 6. So that one probably made a little more sense in what actually happened there. This dividing by a fraction is multiplying by its reciprocal is maybe not something you're as comfortable with, but it still does apply. It still does work, and that's still the answer. Now on these last two, I want to reiterate that whatever, because I'm going to set these next ones up as proportions, I'd like to reiterate that 35 over 21 is the same thing as 15 over 9. Those were equal in proportions, which is, of course, that 5/3. And as an enlargement goes right here, 28 over 12 over 6 is the same as 28 over 14, which is 2. 2 over 1. 2 to 1, if you want to consider it like that. These are all in proportion with each other. So on numbers 27 and 28, let's talk proportions on these. Maybe it'll help you make better sense of what it is that it is. Actually, this one's really easy. I don't even need to calculate anything. But number 27, we're going from blue to red. Just keep that in mind. From blue to red is a reduction. We're dividing red by blue corresponding. K is 2/3. And y, listen, y is 3. I think we can all agree that y is 3. But these are, I don't know if they're equilateral triangles, but they're at least isosceles. From 3 to 2, from 3 to 2 on both of those. I'm not going to do more work than I need to on a problem like that. Number 28. Well, it looks like 25 was the hardest of the problems here. Number 28, I want to at least set up the proportions so you see what it looks like, but we do go from blue to red, so we are doing a reduction. So we're going to divide 7 by 28 to get 1/4. Now let's ignore the 1/4. Well, let's ignore the 1/4 for a moment. It's very practical and beneficial, but let's work on what we have in the diagram here to work off of here. Whatever m divided by 4 is, 28 divided by 7 is. Or whatever 4 divided by m is, 7 divided by 28 is. Or whatever 4 divided by 7 is, m divided by 28 is. This is how proportions work. And I'm probably speaking beyond what this is requiring you to do, but I want to make very much mention of that. M divided by 4, as those parts correspond, is the same thing as 28 over 7. Does this have to do with scale factor? No, this is just strictly in solving for the variable. Now I could cross multiply, and I will. It's not, I should reduce a fraction. 28 over 7 is 4. But just to kind of tell you what we're going to be doing in the future and what the first problem would have been good with, proportions and cross multiplication. 4 times 28 is 112, and then divide by 7, you get m is 16. So that's the M value. How many other ways could have we done it? Let's take the 1/4 idea, exactly what we did before. I'm going to take M times some 1/4 and get 4. 1/4 of M is 4, multiply both sides by 4, and you get M is 16. Right, there are a bunch of different ways you can do it. 28 over 7 is 4. I mean, listen, it's all within. It's all within. If I had the one answer to this thing, or there's one answer. If I had the one approach to answer this question, I'd tell you the one. But they all work. And I'll tell you what, proportions is the biggest key to similarity that we're going to do later in the chapter. So understanding what proportionality is a nice gesture to it. And that starts probably in IM1. So when I bring it up, it's, hey, you've taken IM1. It might have been a while, but you've taken IM1. So if I say something on proportions, hopefully we can feel out what it is. And if they talk about proportions later, I'll be prepared to teach it more. All right, number 29, finding a scale factor. You receive wallet-sized photos for your school picture. The photo is 2.5 inches by 3.5 inches. You decide to dilate the photo to 5 inches by 7 inches at the store. What is the scale factor of this dilation? So your original photo is 2.5 by 3.5. So you're looking at 2.5 by 3.5. And then we dilate it. Let's call this P. We dilate it to P prime, which is now 5 and 7. Well, this is the same kind of thing, right? This is a dilation, at least there's maybe not a center, unless the center is right in the middle. But there's a similarity aspect to this, that these grow by the same amount. That whatever 5 divided by 2.5 is, 7 divided by 3.5 better be the same thing. And it is. This is all 2. The scale factor is 2. That's the enlargement, and it is an enlargement. That's what number 29 is. Number 30, another finding scale factor. Your visually impaired friend asked you to enlarge your notes from class so he can study. You took notes on 8.5 inch by 11 inch paper. The enlarged copy has a smaller side with a length of 10 inches. What is the scale factor of the dilation? Now, they aren't asking for the whole thing, but we have an 8.5 by 11. Let's call that P once again. Look, those are our notes as P. And in P prime, the smaller length is now 10. This is some unknown. And honestly, it doesn't matter. They're not asking you for more than that unless they do later. But we're going from 8.5 to 10. What is that scale factor? What are we multiplying by for that? So, once again, it's an enlargement. We're dividing 10 by 8.5. And if I knew off the top of my head, well, I don't. I'm going to multiply both sides, top and bottom, by 2 to get 20 over 17. Yeah, it's 20 over 17. That's the number. And it's not a pretty decimal, so I wouldn't go into the decimal version of that. But that is the scale factor of the dilation there. So 11 times 20 over 17 would be some weird fraction. Maybe that's why they're not asking you to use that. But they could have also used prettier numbers, I suppose. All right, number 31. So those were kind of faster sets of problems. Number 31 to 34. You are using a magnifying glass. Use the length of the insect and the magnification level to determine the length of the image seen through the magnifying glass. So this is as straightforward as you can get. A 60 millimeter butterfly, or monarch, whatever the heck it is, moth, I don't care. A 60 millimeter insect is now going to be 5 times larger than it was before. Wait. This is the length of the insect. So for the first one, 60 millimeters times 5 times your K will give you 300 millimeters. I mean, that's all we're doing on these ones here. Unless they're tricking me. 32, magnification 10 times. Oh, I didn't see the thing, Emperor Moth. I totally did not see that. Emperor Moth, K equals 5. The next one, Ladybug, K equals 10. We'll have us do 4.5 millimeters times 10, which is 45 millimeters. They're literally just asking you to multiply. I'm probably doing more than I need to by copying down the problem, but let's do it. Number 33, dragonfly. Dragonfly, K is 20. Let's make it 20 times bigger. I want to make sure that we're doing it that way. I believe a dragonfly itself would be 47 millimeters, which is 4.7 centimeters. I think it makes sense that this is not the magnification. This is just the insect. 47 times 20 millimeters times 20. That's 940 millimeters, almost a meter. Which means that'd be scary to look at. You're looking, let's look at this. Oh my God. It's like it's a meter big. Carpenter ant. At least I'm learning names of insects and stuff. Oh, they are all insects. Carpenter ant. See, I don't even really read the problem even as I read it. K is 15. Not millimeters, 15. So this will be 12. That should be in black. 12 millimeters times 15 is 180 millimeters. After scale factor. Okay. Oh, I didn't change any of these. Sorry. 31, 32, 33, 34. Okay. All right. 35. Analyzing relationships. Use the given actual and magnified lengths to determine which of the following insects were looked at using the same magnifying glass. Explain your reasoning. So I'm not going to copy down all the names of these things. I'll write K sub, are these different letters? Yes. K sub G scale. So what we're doing is comparing scale factors. Which ones? The scale factor of the grasshopper is 15 inches over 2 inches. And by the way, this answer is not in inches. I'm going to actually come up with the decimal equivalents this time, just so I can compare them properly. Unless they don't actually, look at some of these. Okay, maybe not. Let's just write them as fractions. 15 over 2. I'm going to go non-calculator on this guy. All right, there's the grasshopper. Scale factor of the black beetle, we're going to do 4.2 over 0.6. Now, the easiest way to do something like this is, although I know the answer, it's 42 over 6. Just do a decimal shift, and that's 7. That's 7 over 1. 15 over 2 is not the same as 7 over 1. I'm basically going to write the reduced fraction of all of these. So those are not the same magnifying glass. K sub H, let's do 75 over 16 divided by 5/8. Now this is the same thing as doing 75, and by the way, these are inches. Inches over inches and inches over inches. Not that it's going to matter, but inches over inches. This is 75 over 16 times 8 over 5. What's nice about this is we can reduce fractions across. So 8 over 16 is 1/2. 75 over 5 is 15 over 1. So this gives me my 15 over 2. I imagined that was probably the one that would match up. So these are the same. I don't know if those are the only two that are the same. Let's take a look at the monarch butterfly. K sub M is going to be 29.25 over 3.9. Wow. So this is 2925 over 390. And I can divide those at least by 5. And this is going to be tougher than I thought. 3,000 is 600 times 5. Take away 75 is taking away 15. What did I say? 600? So 585. I think that's right. 390 instead of 400 being 80, it's 78. 5 times 78 there. Hope I did that right. These can both divide by at least 3. 78 divided by 3. I said I do no calculator. 26. 585 divided by 3. 600, 200, 15, 195. And there's that one. I want to see if that's actually correct. And that I doubt I can reduce it more because 26. Oh, 13. Hold on. 13. Oh, 13. Hold on. Let's divide these by 13. 26 is 2. And 195 is 15. So 15 over... Hey! All right. You know what? I trust it. 15 over 2. So Which of the following insects were looked at using the same magnifying glass? Explain your reasoning. All but the black beetle. So the grasshopper, I'm going to type this. Nice. Without a calculator. I was about to. The grasshopper, not the black beetle, honeybee, and monarch butterfly were looked at using the same magnifying glass because they have the same scale factor. Only thing I didn't do was put inches on this part with the monarch butterfly. Inches and inches. Anyway, I wanted to mention that, listen, when I divide inches by inches, I just get a constant value. Scale factor does not have units of measurement with it. It takes whatever units you have and multiplies by that amount. Unless it's doing a unit conversion, and we're not really doing that here. Maybe there's a problem where they'll do it later. That is not the bottom of the page, as that was crashing on me. I'm going to take a look at my thing here. My thing still has another hour to go for encoding. Number 36 didn't seem to be too much of an issue as long as it's not stuttering. I sure hope it's not. Number 36, draw a triangle ABC and A prime, B prime, C prime so that this is a dilation of it. Find the center of dilation and explain how you found it. So I make up my own. Okay, I'm gonna make up my own. All right. My center is. I'm just gonna make sure my center is at the origin. So if I draw an ABC. Oh boy, this is. Oh yeah, thought provoking is open ended, huh? So let's put A, B, and C. Sure, A, B, C. All right, so here's A, B, C. I mean, I don't know what they're having me do beyond, like, I'm going to make my own scale factor of 3, stuff like that, because you can do this one of two ways. You can either dilate from the center to create new, or create new and figure out where the center is. So I guess I'm drawing these to one's a dilation of the other. So I'm going to make everything 3 times larger. So from 1, 2, I'm going to make 3, 6. As A prime. From 3, -1, I'm going to make 9, -3 as B prime. And from -2, -2, I'm going to make -6, -6 for C prime. Now, the reason why this and here's the thing, it doesn't have to be dilated at the origin, but that's the easiest way to make a dilation thing that way. Now, I don't know if they meant to just draw them wherever as long as it's a dilation, but that's what I'm doing. Now, how am I going to find my center? Well, for one, I did this with the knowledge that, you know, I'm multiplying everything by that amount, so it's just naturally going to dilate from the origin. And 2, when I draw these points here, through the corresponding points, it dilates at the origin. So I don't know if I did the problem the way they wanted me to. Because listen, you don't have to dilate from an origin. I can make something that's 3 times bigger and put it somewhere else and change its dilation. If you want me to do that, I can do it. But I can't guarantee the center is going to be a beautiful spot either. Center. So hold on. A. Let's write these out. A 1 2. A prime at. So my K is 3. Hold on. K equals 3. I made these up. 3 6. It's not really thought-provoking. B, oh, I'm sorry. B is at 3 -1. B prime is at 9 -3. C is at, I'm glad this thing's not really interfering too much anymore. Don't want to jinx it though. C prime's, oh, there it goes. C prime is at -6, -6. Okay, center is at origin. Now, it's both by intent and because of lines, because lines draw to there. Hopefully you make sense. You can make sense of what I did. I drew lines from C prime through C into the origin, or I probably drew out from the origin, but even still. From B prime through B goes to the origin, from A prime through A goes to the origin. I mean, but this was also by intent. It was the way that I multiplied things out to create it. Kind of a weird question, unless they gave me the actual points. Your friend, reasoning, your friend prints a 4" by 6" photo for you from the school dance. All you have is an 8" by 10" frame. Can you dilate the photo to fit the frame? Explain your reasoning. I mean, not to fit this frame, So here's the problem with this. No. You could do it within it in a way, but it won't fit the frame exactly. No, because the scale factor from 4 to 8, well, that's a 3. 4 to 8 is not the same as the scale factor from 6 to 10. See, you double 4 and you get 8. You double 6 and you get 12, right? So K1, it's not a true scale factor, is 2, and K2 is 5/3. 2 does not equal 5/3. Not the same. Now, I could fit it within. I could just not use all 8 inches. I could go 5/3 bigger than 4 and kind of work it out, but that's not what it was asking. It could ask a question like that later, but we'll see. How do you see it on number 38? Point C is the center of dilation of the images. The scale factor is 1 to 3, or 1/3. Which figure is the original figure? Which figure is the dilated figure? Explain your reasoning. Well, because K is 1/3 and 1/3 is less than 1, this is a reduction. Therefore, the original figure is the big star, and the dilated figure is the little star. Twinkle, twinkle. I'll just leave it like that. Yeah, that's my reasoning. Now, like I said, these points should go straight from there. I mean, we've done enough compass construction to make sense of that, but this should go straight from there to there, things like that. Yeah. And 1/3 the distances, 1/3 the sizes. All right, number 39, mathematical connections. The larger triangle is a dilation of the smaller triangle. Find the values of x and y. All right. 39. So at number 39, if you see the image, we can start with K being, we go from blue to red. So K is 6/2. Look at the bottom parts that correspond, which is 3. This means every length is going to get tripled. This means if I triple my x plus 1 length, I will get my 2x plus 8 length. So 3x plus 3 equals 2x plus 8, or subtract 2 and subtract 3, x equals 5. That's the value of x. Now, y is not going to get tripled. Y is an angle measure. Angle measures are preserved. The scale factor has nothing to do with y whatsoever. You just set these equal. Y plus 16 equals 3y minus 34. They are corresponding parts. They will have congruent angles. A big part that we're going to talk about with similar figures, but also dilations are similar figures. 2y equals, was that 50? And then divide by 2, y equals 25. So that's x and that's y for number 39. I like how the later problems are faster than the other problems, the graphs and compass construction. Number 40, explain why a scale factor of 2 is the same as 200%. 200% means 200% out of 100%, or as a fraction, literally, I want to write this one, handwrite this one, 200% out of 100%. Which is 2. I mean, that's pretty much it. 200% is twice as much as 100%. You're taking twice as much as what you originally had. I'll just write that. You're taking twice as much as you originally had. And yeah, I mean, it's a decimal shift thing. You can divide, literally I just did. You can divide by 100 and figure it out, but that's what that means. That's why 120% was 1.2 and things like that. So that's a good explanation to me. All right, and exercises 41 to 44. Determine whether the dilated figure or the original figure is closer to the center of dilation. Use the given location of the center of dilation and the scale factor K. Now, I thought it might have to do with being on a graph. I was looking for the word origin. So for number 41, center of dilation is inside the figure, K is 3. What are they asking? Whether the dilated figure of the original is closer to center of dilation. I can't think of any instance where it doesn't matter if it's inside or outside. I don't think inside versus outside matters. I don't think inside versus outside matters. Whether my center's outside and I scale outward, or it's inside and I scale outward, like that, this thing is still closer than this is. This is still closer than that is. So that shouldn't matter. That shouldn't matter. Okay. So either way, center of dilation inside the figure, K equals 3. Because K equals 3, it's an enlargement. They don't ask me to explain it, but I'm just going to say it. I'm not going to type it. K is it's an enlargement. So what do they want? The dilated figure, the original figure is closer to the center of dilation. Original figure is closer. Unless I'm missing something, the center of dilation has nothing to do with it. Why is original figure closer? Because it's an enlargement. We enlarge farther out. Let's get these kind of set up first so I can actually just type afterward. 43, 44. Okay. So that's 41. Yeah, what? 42. Maybe there's a conjecture we can make later that, oh, doesn't matter where the center is. Whatever. These are not the answer. I'm just getting things ready. Center of dilation inside the figure, K is 1/2. Now that it's a reduction, the dilated figure is closer. This will make it easier. Number 43, center of dilation's outside the figure. Who cares? I think. Outside the figure, and K is 120%. 120% is more than 100%. Remember, it's 1.2. So the original figure should be closer. Doesn't matter if it's outside or inside the figure. And center of dilation outside the figure. K is 0.1. 0.1 is less than 1, which makes it a reduction. That means the dilated figure is closer. Don't know if I'm mistaking something there, but the inside versus outside should have no bearing on whether something's closer or farther to the center. Okay, let's keep moving forward. Number 45. All right, a little bit of a graph. Dilate the line through 0, 0, and 1, 2 using a scale factor of 2. Let me get a graph thing. Why isn't it copying? There it goes. Okay. 0, the O is at 0, 0, and A is at 1, 2. Now, this is an actual segment. Well, it's a line using a scale factor of 2. Well, O prime is, still going to be at 0, 0. A prime is now going to be at 2, 4. So let's kind of draw those ones out. So boom, and then boom. If really done properly, they're the same line, right? So kind of like that. I'll put this one kind of in the forefront so you can see it. All right, what are the questions? What do you notice about the lengths of AB and A prime, B prime? AB. Oh, I'm looking at the wrong one. What do you notice about the lengths of O prime, A prime, and OA? Well, part A, O prime, A prime is twice as long as OA. All right. Part B, what do you notice about line O prime, A prime, and OA? I didn't draw a whole line, but they are the same line. The line would go forever, right? This is like y equals 2x, basically, as an entire line. So if I did like, I don't know, and I just extend it out even more, boom, boom, like this, and down like that. All right, here would basically be the entire line, if you will. That would be, like that. Well, they're the same line. that goes through those 2 points. That's not changing. All right, that's number 45. Looks like 46 is a similar question. Kind of weird. These are kind of weird questions. We're almost done, aren't we? Go to 51. Oh my goodness. This kind of, the first questions were really long. These questions kind of sped up. I'm sure there's going to be some proof thing at the end that's like, oh my gosh, it's going to keep me that much longer. But we're probably going to beat my encoding that I need for this to be better. Dilate the line through A at 0, 1 and B at 1, 2. Here's A, here's B. Now there's a line that goes through here, right? I'm going to kind of just leave it. Using a scale factor of 1/2. Okay, well this is going to be pretty small. So here's A in and of itself. And here's B, you know, like that. But the scale factor of 1/2 means everything's going to be divided by 2. So A prime, instead of being at 0, 1, will be at 0, 1/2. And B prime, instead of being at 1, 2, will be at 1/2, comma 1. Like that. Did I say that right? 1, 2, yeah. What do you notice about the lengths of A and yada yada? Now, I'm not really doing a big distance formula thing here. I mean, they are scale factor based things, so there's that. I could tell you exactly what they are. But the length of AB quantity squared is 1 squared plus 1 squared. So AB's length is the square root of 2. Now, A prime B prime squared is 1/2 squared plus 1/2 squared. See, did I say that right? Half over, half up? I believe so. 1/2 squared plus 1/2 squared. So that's 1/4 plus 1/4, which is 2/4, which is 1/2. Now, when I take the square root there, A prime B prime is 1 over the square root of 2, which is, when you rationalize the denominator, it's square root of 2 over 2, which is half of the square root of 2. So A prime B prime is half the length of AB instead of twice the length. Now, this totally makes sense because the scale factor was 1/2. What do you notice about line A prime B prime and AB and line AB? Well, it probably doesn't look it because the way that I did this here, they're not the same line, but what they are is, shoot, I don't know. They're clearly not the same line, but what you probably can't tell with this thing is, they're parallel. This goes up 1 over 1. This goes up 1/2 over 1/2. This is number 46. So part A and part B, they're not the same line. The lines aren't the same, but they are parallel. Ooh, I just remembered. I have, normally I make videos after I eat, which is the case here. Oh, but they are parallel. I made some steaks in a different way, sous vide, vacuum seal, and all this kind of stuff. And they're laying in an ice bath right now. Hope the ice doesn't melt yet. That being said, I heard because I ran my ice machine pretty much all night to make sure that it would run the ice bath, and I just heard the ice machine just make a bunch of ice there. All right, number 47. Attending to precision. You are making a blueprint of your house. You measure the lengths of the walls of your room to be 11 feet by 12 feet. When you draw the room on the blueprint, the lengths of the walls are 8.25 inches by 9 inches. What scale factor dilates your room to the blueprint? Well, both of these should be the same if all was done right. So that K, this is a reduction. Now, by the way, you got to be careful here. This is not, actually here, before I do K. 11 feet, this says 11 feet. So this is a unit conversion that we probably want to do first here. 11 feet is 11 times 12, 132 inches. And 12 feet is 144 inches. When you get the same units of measurement, you can do a proper scale factor. So we are going to be doing a K value of 8.25 divided by 132, which should be the same as 9. Oh, these are inches, by the way, now. See, this is why it really helps to be writing these inches. 9 inches divided by 144 inches. Now, I know that this is 1/16. I can only imagine that this is also 1/16. Let me check 8.25 times 16, or 132 divided by 16. 132 divided by 16, 8.25. Okay, so it's 1/16. That's the reduction for the blueprint. Thankfully, I don't have to draw the blueprint, but that is the scale factor. So the tricky part is the thing. See, I can't just do 9 over 12 and say it's 3/4. 3/4 what? It's 3 inches to every 4 feet, but scale factor should be a constant. It shouldn't have a unit conversion within. It could, but that 3/4 is no longer 75%. You know, it doesn't really work that way. All right, making an argument. Your friend claims that dilating figure by 1 is the same as dilating figure by -1 because the original figure will not be enlarged or reduced. Is your friend correct? Explain your reasoning. Sort of. Your friend is correct that the size of the image doesn't change. However, its orientation in space does. The object is no longer exactly where it was before, but rather it's truly a 180-degree rotation about the center. Wait, I'm trying to do the degree sign. 180-degree rotation about the center of dilation. So your friend's kind of correct. If you're talking about congruency and distance from and things like that, yeah, your friend's correct. If you're talking about place and space, orientation, not exactly. So it's yes and no. Yes and no. Your friend kind of has a point to make. Number 49, 3 more questions, and this question has 4 parts. Number 49. Rectangle WXYZ has vertices here. Find the perimeter and area of the rectangle. Dilate. Okay. So this is where we get to talk about perimeter versus area. I suspected this might come up, and here it is. I didn't actually know at this point that it actually still would, but this is where you get to learn about, whenever I say something's twice as large. Oh, scale factor of 3. Uh-oh. All right, I'll have to probably go by 2s here. When I say something's twice as large, I never mean it by area when I say that. I mean it by length when I say that. Area is going to be a little bit different, and we're going to see an example of this right now. And this is a good set of numbers to have. So I'm going to change these by 2s because dilating by 3 is going to have to work that. They also have to do a 1/4 scale factor. So this is, I might have to make multiple graphs. Not really a fan. When I thought I had time past the 2-hour mark. When I thought I had a little less time to go, it just, bam. So W's at -3, -1. X is at -3, 3. Remember, I scaled by 2s. WX. At least this is a 5, 3. At least this is a, horizontal and vertical sets so we can count things a lot easier. They're not going to make me do distance formula things. So here's WXYZ. All right, we'll just go with that. That looks great. Oh, that last one doesn't. Okay, suddenly, when that last one doesn't look great, suddenly I just got to fix everything. You can tell this is when I'm at, I'm checked out mode. This is my 3rd video of the day. Remember that. All right, find the perimeter and area of the rectangle. So these lengths, remember, these go by 2s. Let's just, okay, from -3 to 5, that's 8. And from 3 to -1, that's 4. So perimeter of WXYZ is going to be 2 eighths plus 2 4s, which is 16 plus 8, which is 24 units. The area of WXYZ is 8 by 4, which is 32. Now, these are units, these are square units, but whatever, there's that. All right. Dilate the rectangle using a scale factor of 3. Find the perimeter and area of the dilated rectangle. Compare with the original rectangle. What do you notice? So you are going to notice something very unique about this when we get there. So WXYZ, or W prime, is going to be at -9, -3. Let's see. W prime is at -9, -3. X prime will be at -9, 9. Y prime, multiplying everything by 3. Y prime will be at 15, 9. And Z prime will be at 15, -3. So -9, -3. -9, 9. Too bad they scale by 2s, and these are all odd numbers. They really, they can't help themselves. That's the thing I always have to kind of be about. 15, 9, and then 15, -3. Okay, so maybe I can fit the 1/4 on here. Just pretend like I know what I'm doing with it. I mean, they're really mean with that, with the quarters, because just dumb. Sorry. I'll tell you what, they never did ask you to graph it. They just said dilate it. They never did ask you to graph it. So I might go without graphing the next one, if that's okay. Listen, this is going to now be 3 times bigger. This is 24. This goes from -9 to 15. That length is 24. 3 times bigger here is 12, from 9 to -3. That's going to be 12. So now when we do perimeter here, perimeter of W, this is part B, WXYZ, prime. This is going to be 2 24s plus 2 12s, which is 48 plus 24, which is 72. This is part B. This was part A. The area of W prime, X prime, Y prime, Z prime is 24 by 12. 24 times 12, which is 288. Now, to compare, we've done a lot with scale factors, right? To compare these things is to do a division. We can divide the perimeter of one by the perimeter of the other, the area of one divided by the area of the other. And we're going to notice something a little unique here. So the perimeter of WXYZ prime divided by the perimeter of WXYZ is 72 over 24, which is 3. That matches with the scale factor. Area, however, is a little different. Area W prime, X prime, Y prime, Z prime divided by area of WXYZ is 288 over 32, which is 9. What do I notice? The area is not the same as the scale factor as the perimeter was. So perimeter is comparing lengths. Area is comparing 2 different dimensions of things. The area is not the same as the scale factor like the perimeter is. Because perimeter may span multiple directions, but its units are measured in lengths. That's one-dimensional stuff. It is the square of the scale factor. That is letter B. And that is, I'm telling you that's how it works out. That is how it works out. That's what you do. Let's do letter C. Oh, I already answered part D. Make a conjecture about perimeter area. So I kind of answered it. That's okay. Repeat part B with 1/4. Okay, this time I'm just going to do, I'm not going to graph it. I'll call it double prime though. Stop, double prime. Multiplying by 1/4 is this. And honestly, I'm not really going to do anything with these because I know what my lengths are supposed to be here. But I'm just showing you what happens when you multiply by the fourths. Or I can still say out loud what they are. 5/4, -1/4. Okay, so the perimeter of W double prime, X double prime, Y double prime, Z double prime. So what you're going to do here is, you're going to take 2 of these plus 2 of these, right? Now, what are the lengths? Before, the lengths were 8 and 4, which is nice. That's pretty good. 8 and 4, we got to take 1/4 of those because now the distance From negative 3/4 to positive 5/4, that's 8/4, which is 2. And 2 is a quarter of 8/4. And we go from 3/4 to negative 1/4, that's a distance of 1. A quarter of 4 is 1. And that's what we're doing there. 2 times 2 plus 2 times 1, that's 4 plus 2, which is 6. And the perimeter, the area of WXYZ double prime is going to be the 2 by 1, which is 2. So once again, not the same. This time I'm just going to say they're not the same, and I'm going to repeat the conjectures before. The perimeter is the same as the scale factor. Excuse me, I'm not done. Let me actually write out how they are comparing. So perimeter compared to the original perimeter. So perimeter of the new W double prime, X double prime, Y double prime, Z double prime. It's a good question. It's just the weird numbers here, especially when they could have done that better. So this is 6 over 24, which is 1/4. That seems to match up. The area is 2 over 32, which is 1/16. Now, I made the conjecture once more before, and I'm going to be saying it again here, but the perimeter is the same, whereas the area is different. I'll just say the perimeter is the same and the area is different. Smaller. Same as the scale factor. The area is small. All right, part D really kind of asks you to take this thing home and make a conjecture. Now, I just said it before, and I'll say it again. When before the scale factor was 3 for the length and the perimeter, now the scale factor is 9. When before the scale factor was 1/4 for the length and the perimeter, now the scale factor is 1/16. The scale factor, the ratio of perimeters, my conjecture, and it's true, the ratio of perimeters matches the scale factor. Exactly. Whereas the ratio of areas is the square of the scale factor. The reason for this is because you're spanning multiple dimensions when you talk about area. And the best thing I can do and show you, I'm sure we're going to do it later. I mentioned this about TVs sort of before. I have a widescreen television. The aspect ratio is 16:9, like this. Let's say you want to double it. Let's say I want to double this television. What does it mean to double the television? Double the lengths? Okay. Well, let's say that this is double the lengths, right? Looks like the American flag. This is double the lengths. Does that mean it's twice as big a TV? Not necessarily. How many TVs can you fit in here? 4 of them. 1, 2, 3, 4. Clearly it's not made to scale, but you know what I mean. You can fit 4 of those in there. So while you doubled the lengths, you doubled 2 different sets of lengths, widths, and heights. So the area isn't twice as big. The area is 4 times as big. The square of 2. And that's how that thing works. I'm not going to get deeper into that. But if you tripled the length of a television, then you can fit 9 of the TVs in there because you're doing 2 different dimensions of them. Anyway, that's a big thing to hit home for that later. All right, number 50. You put a reduction of a page on the original page. Explain why there is a point that is in the same place on both pages. Because somewhere there's a center. Somewhere exists a center of dilation. And that center represents where everything enlarges / reduces. Oh, in this case, reduces toward, which means that point will be unchanged. Now, this is true. We've seen this a couple times. We've done it with compass construction. We've done it with graphs. If there's a point that's on the origin, it stayed on the origin. I think we had that with an L or something like that. From the compass construction, we dilated from like M to make M prime and something like that, and it's been on the same point. Same thing with a page. If I have something and shrink to and from that thing, you can do this on Photoshop, by the way. You can pick an anchor point to grow and reduce from, to rotate from, things like that. it'll just stay there. Nothing else changes from that. So that's just the reason. Last one on reasoning. Triangle ABC has vertices here. Find the coordinates of the vertices of the image after dilation with center at 4, 0, and a scale factor of 2. So it's the last question, but this is the first one where and I don't know if I have to change scales. I'm going to say you don't have to probably too much. I'm probably going to keep them as they are. But right here, ABC, let's start with that. 4, 2. A and B is 4, 6, and C is 7, 2. Whoa, A, B, C. Now, here's the thing. We're not dilating from the origin. So a scale factor of 2 is great, but that doesn't mean that you multiply these numbers here by 2. You don't multiply 4 and 2 and 4 and 6, 7, 2 by 2. Your center's now at 4, 0. So if you want to multiply anything by 2, you can, but this is the center. But it's not those. You're multiplying the distances here. You're multiplying those things by 2. So when A gets doubled, see this distance here is 0 on X and 2 up. A prime is going to be where C is. Here's A prime. B is 1, 2, 3 away and 2 up. Well, it's double that. 4, 5, 6 away and 3, 4, like that. Oh, B is at 4, 6. What did I do? Hold on. I didn't mess everything up, but I messed a little bit up. Let's redo that. I messed that up. B is at 4, 6. B and C are in the wrong spot, and B was literally in the wrong spot. C is at 7, 2. Okay, let's do that again. So I'm just going to kind of boom, boom, boom. Okay, so A doubled from 4, 0. Once again, I'll call this center. A prime is going to be double that distance from here, not from the origin, but from there. C prime is 1, 2, 3, 1, 2. So 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4 up. There we go. That's better. And B prime is 6 up. Now we got to go 12 up from there. And there's B prime. So it's a dilation, but different spots that it's going to. Not the same as from the center. Because you can imagine, I could still be able to draw. I mean, you know what this is like. We did it with compass construction, if you did do it with me on compass construction. But everything grows from this center now, not from the origin, but from there. So find the coordinates of the vertices now. A prime. A prime is now at 4, 4. Maybe that's what I was thinking about. B prime is at 4, 12. And C prime is at 10, 4. You know what really saved me on a lot of these problems is I didn't have to do a lot of explain. And this is among the ones I didn't have to do any explanation on. All right, I think that's the last problem. And yep, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. And I sure hope this isn't as chuggalicious as it seems it may be. I apologize if it is. Listen, this is my 3rd video today, and all the other ones are in coding, so blah, it just had to happen. So guys, take care. I will see you in the next one.